Okay. So today we're looking at a few cool fluid examples. I've got them kind of scattered. This is just my water. But I've got them kind of scattered around here, so we can take a look at them. I know we're all socially distant away from each other, but hopefully you'll be able to see those, well, what we're about to do, and we'd hopefully have a good conversation about them and kind of figure out what's going on. So I'd like to first start off with this big boy. On the inside there is a little squid creature. I don't know if Noah can see that all the way in the back. It's a little green guy. Do you see the little green guy? Squint your eyes as much as possible.
Nice. I didn't realize
Okay.
it was at the top of the bottle.
There's the green guy at the top of the bottle here. And it's just a classic little thing here. What I'm going to do is I'm going to take this and I'm just going to squeeze. Whoop.
Guten Tag.
Guten Tag, you're interrupting my video, yeah.
Sorry.
I don't know.
Look at the squid.
Look at the squid! Oh! Whoop.
That is amazing.
It's probably the most amazing thing that's ever happened.
Anyway.
You squeeze, and then whoop, just like that. Thoughts on how this works?
Pressure's in there somewhere.
Oh, you know pressure's got to be in there somewhere.
How does it go under?
Squeeze.
Wait, how does it go?
Squeeze.
He squeezes.
Whoop.
So it's completely full up to the top.
The big bottle?
Yeah.
The big bottle is full all the way up to the top.
Is there any air?
There's no air inside the big bottle.
The water can't be compressed.
Correct.
Is it stretching the bottle by chance?
Nope. Thoughts, Nate?
Whenever you squeeze the bottom of the bottle, it causes it to move around a little bit, making lower pressure.
But it's in compression.
So, to Gio, your first question, is there any air in here? In terms of the big bottle? No.
The cap?
In terms of the squid?
Okay, so is the squid a sponge? Is that what's on the top of it?
It's not a sponge.
Is it
Squid.
rubber? What's on the top?
It's a squid.
Okay, got it.
The squid is made with a little pipette.
Oh, okay. So the water has nowhere to go, and since water is whatever, you know the word.
The word he's going for is incompressible.
Yes, that's the one. So when you squeeze it, it's the pressure from the water that you're exerting on the outside is being exerted instead onto the pipette, which is sucking in the water.
Don't say suck, not a word.
It pulls in the water.
Not pulls, not a word.
Suck, yeah, what he said.
Does not absorb, sponges
God.
absorb.
The word where it puts things from here and pulls them into this.
It's not pulling.
What's the word? Displaces?
We are pushing the water into the pipette.
It's like the fan.
I'm squeezing.
That sucks.
That's not what it pushes.
I'm squeezing. I'm pushing that water into the pipette.
Which makes it go up inside, and then it sinks because it's the
We filled up the pipette with water. So yeah, that's what's going on here. It's just a pipette. The pipette's got a little bit of air in it. When I squeeze this, the water is incompressible, so the water's got to go somewhere. It compresses the air that's in there, increasing the overall density of the pipette. Eventually, because there's a little mass on the bottom, the pipette becomes dense enough, or it has more weight in the buoyant force. It sinks, and when I let go, that water whoop, slips out of the pipette, and it floats again. So, wing! And this is commonly known as a Cartesian diver. And I think I hurt my hand doing that.
Watch. What happens if the squid flips upside down?
If the squid flips upside down, what will happen?
If you apply pressure, won't it fill up with water, or will it actually? Yeah, the air from the inside will go up to the top, right? If you squeeze it and apply pressure.
What do we
Then it
think?
will sink to the bottom.
What do we think? What'll happen if that squid's upside down instead?
Nothing will happen.
Mikey?
I don't think there will be a change because when you're squeezing the bottle and forcing the water into the pipette, I feel that because it is so full, there would be no room for the water for the air to escape from. So it would just be an upside down squid doing the same exact behavior.
I'll say it rotates because the top part is less dense.
What direction does pressure act?
Everywhere.
In every direction. So if the squid gets flipped upside down, as long as that pipette is still in the water so that it's, this is completely filled up, like I filled this up to the brim. As long as that pipette still has the opportunity for water to enter into it, doesn't matter what direction you have it facing. It will sink, and it will rise back up. Okay? So, kind of a neat thing there. The key is that, even that top surface of the pipette has to be underwater. If for some reason that pipette is floating and the top is out of the water, then when you squeeze, you're actually just going to raise the water level, but at some point you're going to get it above the pipette, and you're going to push it in. So, that's what's going on there.
So even if it's upside down, you can't displace the air into the bottle and make it go to the top, and then the air that it displaces will be sucked up.
Let's see if I can get this out in one go. Squid. Squid upside down. I'm getting all my papers wet. And it wants to flip because there's a weight on the bottom. But in general, it should still just fall. Yeah, because even if there's a gap in the top of that water there, or in the top of this, you'll squeeze it until the water gets to the top, and then it'll go over and then drop down. So pressure is a scalar, it acts in every direction, doesn't matter. But this is the Cartesian diver. Cool little thing there. Often done in like middle school science fairs to show buoyancy and pressures. So neat thing. Second thing we got to see, and you might have seen this. I don't know if you've seen this or not in your life, but I'm kind of magical. We know that this water down here has weight. There's a hole right here, so when I flip it, the water should really go through the hole, but it didn't.
I think I understand.
The juices are stuck.
Is it because the air wants to get past the water so much, and since the hole is so tiny, that the force that the air wants to go up and the force that the water wants to go down do each other, since the water is going to be applying pressure to the
Yeah. There's a pressure down here trying to get up through the tiny hole. That water is preventing it from doing so, but that air is pushing it back up. If I allow this system to work by kind of squeezing and then changing pressure, pushing some air up, which will flow to the top, and then allowing that to go back down, I can start getting water into the bottom. Now, that's like a really terrible way to get the water to the bottom. A better way to do it is a little spinny action. We built a little twister, a little vortex on the inside of that. And what's actually happening there is we get a funnel of air that runs from the hole all the way to the top. And when that occurs, we don't have an issue of a pressure building up on one side. We're able to move air and keep these pressures equal so that the water in its weight can just flow down to the other side. So if you ever have a lot of liquid and you need to empty it, creating a little vortex is the fastest way to do it. It's the fastest way to get air out of things, especially if you've got like a big 2 liter like this. If I can make a vortex inside of there, which depending on your system, it's kind of hard to do, that's the fastest way to do it. I love this one though, as a little vortex action, and then it's just gone. It's a fun one. Ching! Now this one is super weird. So I'll kind of describe what's going on here. Bottle of water, no water up top. There's a straw here going down, and then a straw on the top side. When I flip this over, the water from the top is going to go down, but it's also going to make a fountain effect coming out of the top. So you can see the splashing happening up here, or on the board. I don't know. This is like an old Greek fountain. How's that magic happening? Brett, thoughts?
So when you're initially flipping it over, the pressure's going to equalize themselves by going through the straws, and then when the water gets to the bottom, it's taking the water with it, and then it's following through with capillary action.
So there can't be any capillary action here because that water can't get absorbed into anything.
Oh, that's the wrong term. It's just cohesion. It wants to follow itself.
So you're saying the water wants to follow itself all the way up?
Yes, and with the pressure combined with that, it's going until it's equalized.
That'd be a long way for the water to go by itself, just attached to itself like that.
Well, I'm saying the pressure's going with it.
So you're saying that there's a pressure change between these? What if I told you this? If I cut the top off of this would still happen.
And I'm at a loss, and I have to think of a new idea.
Because the only reason this top is here is so I don't make a mess. One year I cut it off and it was messy. Thoughts, Gio?
So the weight of the water at the bottom is pushing up into the straw, and since there's more weight being added as it goes, it increasingly applies pressure, not pressure, but a force down, and the way for that to escape is instead of going up, pushing up against the wall of the bottle like you would normally, it has a way to escape up the tube, the force of the water following and the weight of the water, the rest of the weight of the water will push it up to the top.
Okay, I like that idea. You're pushing air out of the way here, and the air's got to go somewhere, so it goes up and it brings water with it.
I wasn't thinking the air. I'm thinking.
You're thinking the water?
itself. So the water on top flows, and it gets to here. Then you have the tube. Once it starts to fill into the tube, because that's how straws work, they just kind of stay at the same level. Since you have more water falling into it, it will push up against the water from the top will fall and apply force down to the water below, which since water is incompressible, it will let the force keep traveling. And since the force has a way to escape through pushing the water up and out, that's how it will push.
That's a neat idea, but there's two straws here.
No.
They're two separate straws. Bum, bum, bum. There's a trick here. There's something you can't see. Something really subtle. You're close. Like 80% of the way there. Nate?
Is maybe some of the water. Is there like a gap? Like, are the two holes connected in some way where the water can get into both sides? I can't see like tell from the thing. Like, is there a way for the water to get into the straw from the top?
Is there a way for the water to get into the straw from the top?
And then the air is going up and shooting it out.
There are tiny holes in the side of the straw here at the bottom. So tiny that you can't even see them right now. You can only kind of feel them when you run your hand across. But, unpause. So there are tiny holes at the top, or at the bottom of the straw here, such that everything that you wanted to happen, Gio, is occurring, but just on different straws. When we tip this over, as this water falls down, it's displacing air down here. So if left to its own devices, there'd be a pressure buildup. Well, it doesn't want that. So we send this pressure up the other side. But, through the straw. But since there's water in the straw, because there's a little hole there, we take some of that water and we lift it up with that pressure, and it shoots out the top. Makes a lovely little fountain. So, kind of neat thing there. a little fountain system set up. This is another cool thing that we see in the world of fluids and looking at pressures. All sorts of neat kind of clever things you can do. Tom? Cool beans.
Can you funnel this?
Can I what?
Can you make the funnel, the water funnel?
I cannot funnel this. I tried earlier. I literally have been trying for years, like, can I funnel? Like, you can kind of funnel it, so it's, like, draining faster. But the weird part is that, like,
It's still dry.
you only have a small hole here that it's going through, and then this is in the way, so it's causing, like, a turbulent effect. So you never get, like, a good funnel out of it.
You did it for like a second.
It just, like,
try.
kind of does it. Now, the real question is, if I could funnel it well, is the rate at which the water comes up more or less out of this? And the key would be it'd be less out of this, but slightly, because we no longer have as nice as a pressure buildup because the pressure is equalized throughout all of it. But it's kind of hard to see that and it doesn't really look well. But that is the idea of the fountain. So another cool thing there as well. Questions regarding either the Cartesian diver, our vortex, or our fountain? Tom?
You said that the ancient Greeks used it, right?
Yeah, you can do stuff like this with the ancient Greeks.
So, don't those fountains, like, constantly go? Like, they're indefinite?
You mean the ancient Greeks fountain, aren't they? Don't they go indefinitely? Don't they keep going, going, going?
Yeah.
Yes. What you're not seeing is what occurs underground. Underground, they would typically have people walk in a circle to lift water. If those people can lift water all day, then what you are essentially doing is refilling this top part. Note, this isn't all the way up to the top of the fountain, right? So as long as I can just keep lifting water up into the base of the fountain to get it to fall, this will work. So I put underneath my fountain a kind of Archimedes screw and just have people lift water all day. Geo statement: take 2 fountains and just flip them. So yeah, you have people underneath who just walk around and move water all day.
Is there, like, a possible way to, like, equalize it so that you can have just a certain amount of water that just keeps going through?
Perpetual motion.
No. No, you cannot have a system where you'll just keep getting water to come through. You need some way to pump more water into this top part. Nowadays, that's easy. We just use an electric pump, call it a day. Back then, you'd have to have someone underneath walking in circles to do this, to lift water up with an Archimedes screw. But you need water to get up here. Now, what you could do is, if you built your fountain next to something like, I don't know, a stream, then sure. Like, you could build it so that the stream runs across it. You've got, like, a hole in the ground that leads to, like, an underground portion of the stream that then kicks back up outside, or, like, into a later part, and then you just get a little fountain in the stream. But now you have to kind of design your entire estate around where a stream is, and that becomes more difficult. So, but yeah, that's one way to do it. Now, there's one other thing I'd like to talk about.
Suck.
Suck. Suction cups.
Waiting to hit the bottles.
Yeah, waiting to hit the bottles and knock them everywhere. How do these work?
I learned that sucks.
Why do you talk?
Mikey?
So the solid. Okay, so the suction cup is made out of solid, right? And when you push it, you are changing its form a little bit, and you are creating enough pressure yourself to force air out of it. And then when you release it, it wants to go back to its normal state, but the pressure in it, like what air is left within, is way lower now than the air outside. So there's way less of it, and so the air pressure from the outside is pushing in way more than the air in the inside pushes out, and it sticks it there.
So, if you couldn't hear that, Mikey just said that when I take this and I push it onto this, it's kind of suction cups have that kind of like U shape right here. So when I push it and I push that U in, you're claiming, and correct me if I'm wrong, that when I push that in, I'm pushing the air out, and then because this is now like sealed, there's less pressure on the inside because there's less particles there, and there's more pressure on the outside, and this outside pressure holds that in place.
Yes.
And then Mikey said, yes. And I say, yeah, that's great, Mikey.
Okay.
That's exactly how a suction cup works. It's not suction, it's pushing.
Can't we just let suck exist?
We cannot let suck exist.
Please
Suck
don't
is
let
not a
suck
thing.
exist.
You push. You push.
Please?
So that's what's happening here. The atmosphere is actually pushing on this surface area with a pressure. We know a pressure with an area will give us some sort of force. So that is how a suction cup actually works. How they got the name of suction cup and suck, I had no idea. But the kind of, oh jeez, this one's so good. Ugh. The interesting thing about these is this means that if you try to use these in space, you'd get run out of NASA. Because if you try to use these on a space shuttle in space, there's no atmosphere in space, which means that you lost your suction power.
About to see me go into space with a plunger.
Right? So,
But wait. Even if it's yeah. I was gonna say even if it's like pressed up against the side of Fort Lee's, but there's not pressure out here anymore, so it actually gets sucked off because there's a little bit of pressure.
yeah, even if you took a suction cup and you put it on the side of the rocket before it went up into space, there's a little bit of pressure underneath. It's not a perfect vacuum. And this means that if you took it out into space, that little bit of pressure on the inside is actually the high pressure, because space is the vacuum, and you would you'd push it off. So, interesting thing with suction cups there. It's also interesting with suction cups, while it's hard to pull them directly off the walls, it is much easier to peel them, like that. They've tried to make like baby spill-proof things where they're like mats that sit on counters and whatnot. And the idea is that there's a suction bottom, and you cannot lift them off. They're very difficult. But babies know better than that, and they just peel them off instead, and they throw Cheerios everywhere. Little brats. Anywho, so that's just another interesting thing we see within the world of pressures and fluids. Bye.